Okay, so let us continue our discussion with this new lemma that we were talking about in the last video. So this is an extension, a natural extension of a previous lemma that had the name single choice, whose statement was pretty straightforward. It said that if we have a non-empty set, then there exists an element in it. It looks quite stupid, but nevertheless, from an axiomatic point of view, this is a lemma. And in fact, we proved it, we did it towards the beginning of set theory. Now, this is a natural extension where instead of a single set, we have finitely many sets. How many? That is up to us. That number is not fixed. It can be any number, but at a time there are finitely many sets and all of them are non-empty. Then we have to prove that there exists an n-tuple such that its ith component belongs to the ith set. In other words, if each set xi is non-empty, then this Cartesian product is non-empty because that n-tuple will be an element in this product. So in this case you can see that in case of single choice actually the same statement works. Here instead of an n-tuple, where n is general, we have a one-tuple which belongs to this Cartesian product xi, where I varies from 1 to 1. That means I takes the only value 1. And if where x1 is nothing but x. So when n is 1, the single choice lemma tells us that this statement is actually true, and that gives us a hint as to how to prove it. We will prove by induction, and this is the basis of our induction. So let us see how the proof proceeds. It's very straightforward. We apply induction on n. So when n is 1, the result follows from single choice, but there is a number, lemma 316. That is the single choice lemma. So we have already seen how that follows from single choice. Now we assume our induction hypothesis, namely that the result is true for n number of non-empty sets. Let us assume that the result is true for some positive integer n. Some positive integer n, some arbitrary but fixed positive integer n. Okay. We will now prove it for n plus 1. So we need n plus 1 non-empty sets. So we consider them. Let these be non-empty sets. Now, since the induction hypothesis is available, so we can apply that on the first n non-empty sets. by the induction hypothesis. So what is the statement? The statement is that there exists an n tuple whose ith coordinate belongs to the ith set for every possible I. By the induction hypothesis, there exists an n tuple such that xi belongs to capital Xi for all I lying between 1 and n, inclusive of 1 and n. Okay, now we also have this extra set, the last one, and that is also non-empty. So there we are again going to use Lemma 316 single choice to choose one element from that, since xn plus 1 is non-empty. Lemma 316 implies there exists an element, some element A in xn plus 1. Okay, now using this n tuple and this extra element, we can now create an n plus 1 tuple so that the ith component of that belongs to the ith set in a very obvious manner. We now define the n plus 1 tuple yi, where now I varies from 1 to n plus 1 by this formula. Okay, let me write it here. yi is defined to be equal to xi if I lies between 1 and n, and is defined to be equal to a if I is n plus 1. Okay, so here what we have basically done is this: we already had this n tuple, we now have this n plus 1 tuple, where you can see that okay, this is y1, this is y2, etc., yn, and this is yn plus 1. So you can see that yi belongs to xi when I lies between 1 and n, because in that range of I, yi is actually equal to small xi, which belongs to capital Xi, and yn plus 1 is a, so a belongs to xn plus 1, so yn plus 1 also belongs to xn plus 1, and that's what we needed ultimately to complete the induction. Clearly, yi belongs to xi for all I lying between 1 and n plus 1. This completes the induction. And the proof. So this is a pretty easy consequence of the axioms of set theory. Now you may wonder why only finitely many non-empty sets, why not infinitely many non-empty sets. In fact, that statement also can be considered and will be considered, where you have infinitely many non-empty sets. Although I am writing it like this, the collection of sets, that may not be the case. I mean, you can understand if you already know about countability, uncountability. This is a countable collection of sets where the number of sets is infinite and all of them are non-empty. Then from each one of them you can choose one element to create, if you want to call it, an infinity tuple, or in other words a sequence. That can be done. However, that is not a result in this part of set theory, in the sense that this general statement where the collection of sets is not necessarily finite, this cannot be proved from the axioms of set theory that we have got so far. We have to introduce this statement as a new axiom. It is considered to be true, and that is the axiom of choice. So regarding that, there is a remark. So let us see what the remark says. It is intuitively plausible. It seems to be true that this lemma should be extended to infinitely many non-empty sets. Because from one set we have extended it to any finitely many sets, so naturally we should consider next infinitely many sets. However, this cannot be done without introducing a new axiom, that is the axiom of choice. And we will see this in detail in the 8th chapter, specifically in the 4th section of the 8th chapter. Okay, so here the text part of this section ends, 3.5. Now the exercises begin, and let us see what the exercises have to offer. So the first exercise is quite long, so I will first write it down and then we will discuss. Suppose we define the ordered pair x, y for any objects x and y by the formula okay, then that's using several. Okay, Thus, using several applications of the third axiom, thus for instance 1, 2 is the set two, 1 is this set and 1, 1 is the set which turns out to be nothing but this singleton set consisting of the single set as its element. Okay, show that such a definition indeed obeys property 3.5. We will see what this property is. We have already seen this, but only we have not mentioned this number 3.5. And also whenever x and y are sets, the Cartesian product x cross y is also a set. Thus, this definition can be validly used as a definition of ordered pair. And there is a second part for an additional challenge. Show that the alternate definition x comma y equal to x comma y also verifies 3.5 and is thus also an acceptable definition ordered pair. For this latter task, one needs the axiom of regularity. I need ink. And in particular, exercise, there was one exercise that we already have solved. We will need that. Okay, so what is this thing? Let us look at this exercise. It looks extremely long, but it's actually not that big of a deal. So here we seem to have defined ordered pairs of two objects using sets. Okay, let us recall what we have done so far in this section. We first of all defined ordered pair of two objects. If x and y are two objects given to us, then we defined an ordered pair formed by them to be a new type of object. Much like how we said that a function between two sets is a new type of object. And then what we did, we said that we defined two ordered pairs x comma y and x prime comma y prime to be equal. We defined them to be equal whenever their corresponding components are equal. Okay, so our definition of ordered pair that we have worked with so far before this exercise has been a new type of object. Okay, and this extra definition tells us when two ordered pairs are equal. That gets the job done for us. Then using that definition of an ordered pair, we then proceeded to define Cartesian product of two sets, and then we moved on to n tuple of objects and n-fold Cartesian products. But the one question remains is that since we are treating set theory axiomatically, the question is that whenever x and y are sets, what is the guarantee that x cross y is also a set? You see, we have already come across Russell's paradox that told us that, hold back, every collection is not a set. That even if you think that it's a well-defined collection, things may go wrong and it's not a set. So instead of defining sets at once as a well-defined collection of distinct objects and whatnot, we decided to take the approach of creating or constructing more and more complicated sets from given simple sets whose existence can be assumed to be true, and those assumptions turned out to be our axioms. So from that point of view, is it guaranteed that x cross y is a set? No, because you see, our definition of ordered pair is only itself an assumption that given two objects x and y, such an object exists for which this definition of equality can be made. Okay, and included in that assumption is also the fact that if two sets x and y are given, then their Cartesian product is a set. Now this itself, you can think of it as a new axiom in set theory. in our set theory, besides the axioms that we have got so far. That is fine, but one may question, is it really true? When it comes to axioms, their truth is something we assume. Why that depends on how natural the axiom feels. No one can say for sure that an axiom is true unless it is proved using something more elementary or something else. So from that point of view, although the job is done for us, it's not a very satisfactory state of affairs for us now. What we would like instead is to be able to define this new type of object, an ordered pair, using only the axioms and elements of set theory that we have got so far, prior to the introduction of this concept, and that has been done here. Okay, and this definition of equality of two ordered pairs that we have already got, this is your property 3.5. It's actually the equation number which since we are not writing the equation numbers down from the text, so that's why we failed to see what 3.5 is. So this is 3.5. So now what we have to do, using this definition, okay, so you look at this definition. If x and y are any objects, then we are defining this ordered pair to be this set. Now in forming this set, we have used only the axioms of set theory we have got so far. And what is that axiom that we are again mentioning that we are using this axiom 3.3 again and again several times? This is your axiom of singleton set and pair sets, which says that if a single object is given to us, then there exists a singleton set consisting of that element as its sole element, that object. And the pair set part of this axiom says that if two objects are given to us, then there exists a set which has those objects as its only elements. So first of all, when x is given to us, this singleton set exists. Then for x and y, the two objects, this pair set also exists. So there we have used axiom 3.3 twice, and then again once more when we are forming this final set which has these two objects which themselves are sets. Also keep in mind that we have used axiom 3.1, which says that sets themselves are objects, so they have the potential of becoming elements of other sets. So here this set is an object, this set is also an object, this second set. That's why they can be taken as elements of another set. And then we have used the axiom 3.3 again, the pair set part, to form this set. In doing this, we did not use anything else outside of whatever we have got so far. So now for us, this 1, 2, this ordered pair is actually this set. 2, 1 is this set, and 1, 1 is this set by definition, which ultimately turns out to be this singleton set, whose sole element is again a singleton set. Now what shall we need to be able to say that okay, this definition is fine, you can use it as a definition of ordered pair? The definition that we had of equality of two ordered pairs, that 3.5, that condition is now, since we have defined ordered pairs using set theory, elements of set theory, so now this is not a definition. We have to now prove it as a consequence of this definition, this new definition. Okay, so that's what we have to show here. Show that such a definition indeed obeys property 3.5, that if this is true, then this is true, and conversely. Additionally, we have to show, now we will show, now we no longer have to make this a new assumption. We will be able to show using this new definition of ordered pair that whenever x and y are given sets, then their Cartesian product is actually a set, and in showing this we will use axioms and results of set theory before this point. And there is an additional challenge. instead of using this definition, if we use this slightly different definition where instead of considering the first element as a set itself, we use the object x itself here. This new definition also is, if we take this one as our definition of ordered pair, then the same thing is true. So this can also be used as a definition of ordered pair. You may be perplexed in thinking that are they not two different things? Yes, they are, but the concept of an ordered pair ultimately turns out to be the same. It's like this is one model for an ordered pair, this is another model for an ordered pair. It's like, well, should I mention this at this point? Those of you who are already familiar with the construction of real numbers, they may know that real numbers can be constructed from rational numbers in several different ways. One of them, two of the most popular constructions are the one involving Cauchy sequences and the one involving Dedekind's cuts. Okay, they are entirely different definitions, but they ultimately describe the same concept. Okay, so this is a situation like that. Although the definitions look different, but they are different, only different models for the same concept. And then we have to prove that this also satisfies 3.5. So it can also be used as an acceptable definition of ordered pair. For this latter challenge, one needs the axiom of regularity, and in particular one exercise we already have proved before. We are going to use that. So let us now look at the solution. You may object to this exercise entirely. You will say, what is the need for us to go through this much trouble when we already have the simple definition of ordered pair as a new type of object, and we are not having any problem with that simple definition, although we have to introduce it separately as an axiom. The point is that now there is no guarantee that the Cartesian product of two sets is a set. It's just a new axiom, and it's not that natural. It's not as natural as the other axioms of set theory. So if someone wants to reduce the number of axioms, then that can be done, and that's what we are showing in this exercise. Okay, so the solution, at some parts the solution gets somewhat complicated. Let me just go through it. So first of all, we are considering that other definition for, the one that is not this one. For any objects x and y, we have this. Okay, so we are using this one. Now we are going to verify this. One part is almost obvious, although we have to write down the details. If this is true, then this is true. Okay, so for that, let x prime y prime be objects such that x is equal to x prime and y is equal to y prime. Okay, then by the definition of equality of two sets, we have this and this, they are true statements because x and x prime are equal and so are y and y prime. And this further implies, which imply that these bigger sets are also equal. So this is quite straightforward. We have assumed this and we have proved this. This implies this. So one part of 3.5 is true. Now we come to the converse, and there it's not that obvious. I mean, we have to go through some steps. Conversely, assume